For this week's lab, we're going to expand the capabilities of Visual Basic programming by learning about loops. In particular, we'll learn about this for next loop. Loops are ways of doing processes repeatedly, and they are really one of the hallmarks of computer programs. One of the things, though, at the beginning you have to be aware of is that if you do something repeatedly, an operation many times, then you need to have a way of ending the loop. And when you're writing the program for the first time, it may be that you get into a loop that doesn't end. That really won't be a problem for next loops for the most part, although I guess there are certainly circumstances where it could be. But in any case, if you get into an endless loop, the program will appear to just stop. And so one thing you should just keep in mind is that the escape or the control break keys will end this loop and it'll stop the program. Okay, so here's the syntax for the for next loop. Basically what you're going to do is write code that says for and then a statement that will give a starting value of a variable. So for x is equal to 1, that's the starting point, to this end value. Then you're going to do some kind of action in between the for and the next. So in this simple example, we will start with a value of x equals 0 or x equals 1. Then we will go through this sequence of this very complicated sequence of steps, which in this case really just involves getting the computer to make a beep. And then we will get to the end here. It will increment x from x equals 1 to x equals 2, and then it will go back up here to the beginning and repeat it. So it will do that until x equals 50, and then it will stop. So this little piece of code will make your computer beep 50 times. So really pretty straightforward, but it shows, I think, in a very simple way how this for next loop will behave. So a variation on this would be to use a for next loop shown here, and this illustrates a couple of different concepts. First of all, we can start the loop with a value of the variable that we're going to be incrementing. We can start it really with any value, and we can end it with any value. So here I'm starting it with 2, a value of 2, and ending it when it reaches 10. And in this case, I'm going to be incrementing it by units of 2. The default is to increment by 1. This variable here, by the way, is an integer variable. It has to be an integer. We can't have this number here be anything other than an integer. But here we go 2, 4, 6, 8, 10. The first time through is 2, the next time is 4, and so on. So that's one thing that this illustrates. Another thing is this little line of code here. And what this does is it takes the value of total and it adds to it whatever this variable j is, and then it takes that sum and writes it into the value, or writes it into the variable called total. So what happens is that this way of having total on the right side and on the left side is a way of summing up what the value of total is. So we can use this for counting and for keeping track of how many times something has been done. And here we count in units of 2. So the first time through, we would have, by default, total will be equal to 0, except it's probably a good idea to actually set total equal to 0 at the beginning. But the first time through, j will equal 2, so 2 plus 0 makes total equal to 0, or equal to 2. And then the next time through, j equals 4, so j will equal 4, total is equal to 2, so that sum is 6, and 6 will get written into total. So this, at the end of the second time through, total will have a value of 6. Okay, so we'll see this little line of code many times. Okay, so we can go up in increments of 2 or whatever increments we want. This example shows stepping downwards in increments of -2. So if we start with 16 and want to go down to 2, then we need to tell it specifically to do it in increments of a negative number. In this case, we're doing it in -2. Okay, so that's the basic for next loop. And one thing that I want to point out is that we can nest these loops one inside the other. So here's an example of a subroutine that's used to write variables into a one-dimensional array. So we define a one-dimensional array of double precision variables that has 10 variables in it. And so we can write numbers into those variables, those placeholder locations, with a for next loop. So this starts at I equals 1. It generates the value over on the right hand side of 1 times 10. That gets written into the first location in array, which would be array 1. And then it goes through, and the second location, array 2, has 20 written into it, and so on. So we end up with an array that has indices from 1 to 10, and in it the values are the values that are being stored in that array are whatever the index is times 10. Okay, so just a very simple way to fill an array with a for next loop. So here's an example of a nested array, and in this case what we do is we declare a two-dimensional array. So this has dimensions of 10 columns and 5 rows, so like a 10 by 5 patch on a worksheet. And what we do to write values into that into those locations is we have here, this is a for next loop that is going with by incrementing I, and so this is really the same loop that we had up here. But we see that this loop is within another loop that is for j equals 1 to 5 next j. So what happens is when you go through this, it starts out with j equal to 1, and then it does this loop for I equals 1 to 10 with j being equal to 1. So you would write the you would set that equal to 1, and this increments from 1 to 10. And then once I reaches 10, you're done with this loop. You go to here, j gets incremented to 2, and then you go and you repeat this again for our I equals 1 to 10, with j equal to 2 here. So we're putting it into a different location in a different column in the two-dimensional array, and we're also changing what the calculation is here. This side of the equation is also changing. Okay, so those are examples of some different types of for next loops. We've got a couple of other examples. These are some simple calculations, and the first one will be a calculation that does the factorial. And here is an example of such a function. And the factorial of a number is that number times the number that is one less than it times the number that is one less than that, and so on. So it lends itself to being calculated with a for next loop. So here's the way it works. We have a function, we give it an integer value, and then we have a temporary variable that we say is equal to 1 initially, and then we use a for next loop, and we're going to do this loop n times. So what we do is we say, well, I equals 1, and so we have f temp is equal to 1, so this is 1 times 1 equals 1. Then we do it again for I equals 2, and we have 2 times 1 is equal to 2. So f temp equals 2 the second time around, and then the third time around I equals 3, and it's 3 times 2, and that gets stored, the value of 6 gets stored in f temp, and we cycle through that n times, and that's the calculation of the factorial. Then when we're done, this f temp, this is just a temporary variable that we're using internally within the subroutine, and so when we're done with this loop, f temp equals the value of the factorial, but we need to make sure to write this value into the variable called factorial 1, which is the name of the function, and so this is how we pass the end result back out of the function so it can be used by whatever is calling this function. So there's an example of how we might use this to calculate a factorial. Another example is using this approach to calculate a series. So here is a series for the exponential function, and this is an exact series if we have an infinite number of terms in this series. But for practical matters, we won't do that. We'll truncate this series with a certain number of terms, and so this will really just be an approximation. But nevertheless, this kind of way of calculating functions is a very common thing in computers, and so this will be a way that will we can use a for next loop for this function here. So let me show you an example of this. If we expand this out, then we see that the function looks like that if m equals 3. So here's how I wrote this series. In this example, we'll start off giving it a value of x, and we'll also give it the value of m. Okay, so we recognize this is going to be the evaluation of an infinite series with just a finite number of terms. So what we do is we call this with, and when we call it, we give it the value of x and the value of m, and we start off again. Well, we're going to have this local variable called temp, and we have n defined as an integer, and so here's the loop, and we're going to start off with n equals 0 and go to m. So this for next loop is doing this series here, and temp is going to equal temp plus, and that term there is this right here. So what happens is we're going to go and for each value of n, we calculate this. We add it to the last value that we calculated, and then we write that result into this temporary variable, and then we repeat that. And each time essentially what happens is each time we take the current value of temp and add to it the next value that's calculated from the series, and we do that m times. M is the number of times that we told it to do, and then at the end we take the temporary value, write it into this variable name that's essentially this one here. Okay, and then we'll also calculate the relative error. So those are the different examples, and let's go now and take a look at the Visual Basic implementation. So the thing that I think is useful to do here, and what I would urge you to do, is try these out and do them with the debugger. So I would put in a breakpoint right there, and if you then run this, these subroutines we can run from within Visual Basic. So if we hit this, we'll run it, and we see it runs to here and then stops. So we can put our cursor over top of x, it equals 1, and if we go to up here, if we press F8, then what that means is we'll step into this function here. There's nothing to step into, so if we press F8, we'll just execute this. And when I did that, I suppose you heard that. It makes a little chime. And then if we press F8 again, it goes up here. It doesn't stop here. It goes up and increments x, and you see now x is 2. And so we execute it again, another beep, and when we execute this line, x is now 3. So x is being continuously incremented. So I don't think we need to hear 50 beeps, so I'm going to press F9 and get rid of that breakpoint, and I'm going to press this to reset. Okay, so let's try this one. If we run this, then first time through, total equals 2, because we started off with j equals 2. Then we run through it again. J will oops, sorry. Let's try that again. So there's j equals 2, and then I press F8, and j equals 4. Okay, so j equals 4. We have not yet executed this line, so total still equals 2. J equals 4. Now we're going to evaluate this expression and then write the result, and we're going to assign that number to this variable name. So we execute it, and we see now that total is equal to 6 after we do that line. J is still equal to 4, but when I press F8 again, J gets incremented to 6. There. Total is still equal to 6. We do this expression 6 plus 6, and so the next one is total equals to 12. And then this function also shows that it illustrates this function here, and this is message box. And what this does is when we're finished, it writes to the worksheet a little message box that says the total is, and then it has this variable which is total. So let's try and do that. I'm gonna press F9 to get rid of that breakpoint, and then I'm going to hit this continue that should finish out this subroutine, or this subroutine. So when it finishes, this is the message box that it gives us. So this is kind of handy. It's a way to get results from Visual Basic to be displayed out on the worksheet. Okay, so here's another example. This is just incrementing in a negative way, and I think that that's probably straightforward. We don't really need to take a look at that. Okay, so this one is, this shows the example of another kind of loop. Right now we're just working with for next loops. That's a way of controlling this variable that gets incremented through the loop. There are other ways of doing this. This one shows a do, what's called a do loop, and we'll talk about those loops in another class. So let's just skip over that one. And here's the example of the function that we wrote to calculate the factorial. So it's really following a similar kind of theme. We saw this one when we reviewed the notes, and let's take a look at how it works. So we'll put a breakpoint in, and in this case, in order to run this, we have to go to the worksheet. We can't press this run symbol here. That only works for subroutines. So for this factorial, we're going to go out here to the worksheet, and I have some examples of the factorial here, and these are done with a different program, but this is the factorial one that we're after. So I'm going to just go here to this factorial, and I'm going to put in a space and take it back out and press return. That will then execute this function, and we go through and see that first time through I equals 1, ftemp is equal to 1, and then we can just step through. Next time through I equals 2, and so ftemp is 2. Next time I equals 3, and so ftemp should be 6 after we execute this. Yep, and then next time I equals 4, ftemp is 6, so we get ftemp of 24, and we're done. And now we write that temporary variable into factorial 1, and that value that's in there at the end of this function gets written here onto the worksheet. Okay, so hopefully that's straightforward. Here's exponential, and this does really much the same thing. We saw the example of this code, and here's Visual Basic. The thing that we see is that in this case, when we're doing a series, as we work through this, and let's just run it once here. So these are different versions. So as we run through this, temp starts at 0 the first time through, though. We have this being equal to 1, and so temp is equal to 1. Then as we step through, temp is equal to 1, we evaluate this number, n to the power of 1 times this factorial. And actually this is an example of a function that calls another function. This factorial 1 is the function that we just wrote here. So rather than rewriting it, what I'm doing is just simply calling it, and it returns the value of the factorial for n, and then uses it in this calculation. So well, actually what happened here, this is a good point. I was on this line, I pressed F8, and F8, as we see in debug, is step into. So what that means is that if there is a function in this line, it will go and execute that function. And so that's what's happening here. It goes and does this. If there's a breakpoint in this function, then it stops there. So what I can do, if I don't want to go through all of this this routine here, then I can get rid of that breakpoint and then press this guy, continue, and this will execute the rest of this line, the rest of this subroutine, and take me to this breakpoint. Now I hit F8 again, and this time what I'm going to do, instead of hitting F8 to step into, I'm going to use Shift F8, which will step over. And what that means is that it will execute this line, but it won't go into the subroutines. So I can use Shift F8 to execute this repeatedly to however many times I need to. And I guess this is 5 times, and right now n is 4, so I'll execute it one more time, and then we're done. And there's the value of the exponential that's calculated for this value of x and however many value, whatever the value of m is, however many terms we've requested. So we can go then back to, let me get rid of this. We can go back to the worksheet and see, here's the example of this is the e to the x power, and I just use the worksheet function right here to calculate that. And then these are different calls to the function that I just showed you. And what I'm doing here is, with each one of these calls, I'm using this value of x, and this value I'm using for m. So I have different values of x and different number of terms in the series. And what this shows is that if we, let me see, so let me get this so we can see all these terms here. This is the value that is calculated by the worksheet. So this is probably accurate to at least this many significant figures. And although, by the way, this is a function that is done somewhat like the function that we just saw. So this is a numerical approximation as well, but presumably they're using a high accuracy function, and it's going to be accurate to at least this number of significant digits, probably quite a few more. But what we can see is that for this value of x, the number of terms that we use in the series is going to improve the accuracy, and we got 27182. So we go out here, and 5 terms, there's 27180, and here's 27182. So we have 6 terms, and we get it to 4 digits to the right of the decimal. And so that's pretty good, but we look down here for x equals 5. If we take the same number of terms, then the exact value, or the accurate value, is 148, but the value that we calculate with this series approximation is only 128. And so what we see is that we need to add more terms with this larger value of x. Here with 10 terms we have 146, and so we're getting closer. And so what this means is that the number of terms that we would use for a certain level of accuracy is going to depend on the value of x, and we could show that with calculations of the relative error down here. So this is x and m. Here's the value from the worksheet, and this is the value that was calculated with the function that we just wrote and the relative error. So for x equals, I guess x equals 5, m equals 5, then you can see there's our approximate value. It's 38% low, which is really not so good. But if we increase this to 10, so this is 10 terms in the series, then we're closer, and we could increase it to 20. And now we're really quite good. 10 to the minus 8 as the relative error. Okay, so that just gives an illustration of how the accuracy of this series really depends on x and of course on the number of terms. So right now, the way we're doing this, we have to tell it how many terms we want, and that's fine so long as we tell it plenty of terms. But down the road, we're going to want to have a way for the function to judge how many terms it should use, and we'll get to that later. Okay, so let's go back to the assignment. So what I want you to do for the assignment is to really go through these different things that we've just seen. Write your own function to calculate the factorial, and go to the worksheet and demonstrate that this is functioning properly. You can calculate the relative error, use some method to show that you're basically to validate that your function is working properly. And then use that technique that I showed you for the exponential to calculate this function. So the log of x divided by x minus 1 is approximated by this simple series. And so go ahead and write this series for a certain number of terms that you specify. And then what I want you to do is essentially set up something like this, where you calculate the exact value, and then you calculate the approximate value for a certain number of terms, and answer this particular question: how many terms you need in the series when x equals 4 to have the relative error less than that value. And then the final one is, well, the next to final one is to do a nested loop where you fill a variable, fill a two-dimensional array with this function. And there's an example of that in the Visual Basic. It's right down here. So here's a function that fills a two-dimensional array with this simple, or a subroutine that fills the two-dimensional array with this simple function. And so since you need to do this yourself, let me show you how this works and how to verify that it's working. So it's a subroutine, so we can run it. So I'm going to run it to there. And the thing that we really need to do at this point is to take this two-dimensional array that's 10 by 5 and make it use a watch so we can see what's inside it. So we add that watch, and expand it out here. So there's the array for these different values of the column. So what I'll do, let me show you how this works. We're gonna I'm gonna hit F8 and go through this, and what I can do, I'm not seeing anything here because it's a two-dimensional array. This is just showing one of the columns, and I have to expand it to see what is in there. So now we see the array with the column and row indices in it, and as I go through this, I'm writing different values to it. So I've written 1 1, and then if I go down here, here's the value for 2 1, and then the array at the indices 3 1 is right here. So I go all the way down, and let me see. Right now I is equal to 9. So we should have, and we've gone through it, so we should have just written the value for 9 1 in there, but we haven't yet done it for 10. Okay, so we'll go through, and now I is equal to 10. And so we execute that, and now it writes it into that location. Okay, so that's going through this first loop, and now we should be done with that loop. And we go out of the loop. J is 1, but we're going to increment J. Now J is equal to 2. And we go through, and we're going to do the same thing for J equals 2. So J equals 2, I equals 1. That's going to be up here. That's going to be right there. And so we write the value that we calculate from this simple expression at that location. And we go down, and here it is at at 2, 2, and 3, 2 will be down here. Okay, so you get the idea. We go through it 10 times, and then we go out, and we're going to increment J and go back up here, and this next time we run it, we'll write it in here. Okay, so we go through this. This loop goes through the array 10 times, and then we do that 5 times. So this nested array goes and does 50 different calculations and writes the results into this two-dimensional array. Okay, so what I want you to do is the same kind of a procedure, but using a slightly different function, and verify that these results are in fact correct. And I would do it at this point just using the watch window. So a good way to do it, I think, would be you can use the watch window and then just use a screen capture that shows these numbers here. Maybe you can bring it up like that. Shows these numbers to verify that it's writing the correct values. And then finally, what I want you to do is go back to section 2 from last week, and what I want you to be able to do there is to calculate the gradient function of that function that we used with that was a log of the distance from the well. Calculate the gradient with respect to x using a function that calls the hydraulic head function. So this was actually part of the assignment, and I know several of you did it, but several of you seem to have not really been quite clear about what was needed. So I'm going to point this out in particular this time, and what you need to be able to do is calculate the gradient, the head gradient, and do it in a way that doesn't really have to access those head values in the worksheet, which is how we did it when we looked at this in class. And the approach is pretty straightforward. You have a function that calculates the hydraulic head, and so you just will call that function from within the function that calculates the head gradient. And so that's that gives you then the versatility to calculate the gradient in a standalone way, and you don't have to go and calculate the heads first in a separate place on the worksheet. You can just calculate the gradient correctly. And to just give you a quick illustration of how this works, here's the function that's head gradient in x, and what I do is have the parameters up here. These are all the same parameters out to here. These are all the same parameters that I used in the function that calculates the head. So I've got a function up here, time plus regional, that has all these parameters in it. And what I did was just copied that parameter list down here for this function and added to it here at the end del x. So now what happens when I calculate this function, when I call it, I first go in here and calculate or call time plus regional, and then here are all the parameters that that function needs, and I calculate the head value at x plus delta x, and I write it into this local variable, and then I repeat that and calculate the head at x minus delta x, and I write that into this local variable, and then I call another function that does the gradient calculation, and that's shown right here. I pass into it h1, h2, and del x, and it just takes the difference and divides by del x. So the only thing here that you need to recognize is that del x is the distance between the points. So if I use a finite difference, a centered finite difference, then this calculation needs to use 2 del x. Okay, then that result gets written into this this variable that's the same as the name of the function. Okay, so go ahead and write an example of a function that does this. The reason for this is because this is getting you to start to write functions that call other functions. And if you can do that, then you can make functions that are very powerful but are relatively compact and pretty easy to understand what they're doing. This function, it really only has 3 lines, but it's doing quite a lot of calculations by calling these in these particular functions. And so you can have functions calling other functions. This leverages the work that you've done, allows you to reuse functions, and it also improves the clarity of the codes that you're writing.